Hello everyone and welcome to this complete machine learning tutorial for beginners. This tutorial is a free preview from the course titled Practical Deep Learning with Keras and Python, and it is available in the complete data science course bundle on my website. In this course, you will learn how to apply machine learning techniques to real-world problems, including how to build a complete pipeline using Keras and Python. If you enjoy this video and would like to continue learning with us, feel free to check out this 6-course bundle, which will take you from beginner to advanced in data science, machine learning, and neural networks. I will include timestamps and links to additional resources in the description of this video, so without further ado, let's get started.
Hi and welcome back. Let's start with a little bit of definition of machine learning. We're going to skirt away from the philosophical aspects of what learning is and whether machines can learn or not. We're going to define machine learning in a much more practical way. So we'll define it as adapting to perform a task in a better way with experience. So better is going to be according to some measure. We'll come to that in a minute. Also, we're going to have some experiences because of which the machine is going to perform the task better. Right? So that's going to be our working definition, and essentially that is what's going to help us do a lot of things. Now, it should come to your mind what deep learning is. If you're not really familiar with deep learning, it's an algorithm in machine learning. So the general aspect is machine learning and the specific concept is the algorithm of deep learning, and this algorithm has shown immense levels of success. So in a couple of minutes we'll get to deep learning really quickly, but the essence to understand is that it's not as difficult as people make it out to be. It's a very simple concept to get started with. It's a lot easier than other models. It's a little difficult to understand why it works, but we don't have to understand the why for it to start working for us in real life. Right? So keep that in mind, that even though nobody really understands how deep learning works, that's not stopping us from getting benefit from it. Right? So what can you do? What kind of benefits can you get from deep learning and machine learning in general? So for instance, you can predict the expected selling price of a house. So this is going to be predicting a real value, right? So real numbered value. Right? So by the way, I use this pen tablet because it has been shown that doing annotations on screen helps students learn. So this is not me trying to get away from animating my slides. It really does benefit the students a lot more if we do annotations as we speak. We can also predict whether a patient has cancer given the information that we have about the patient, for instance, their CT scans. Right? So this is going to be predicting a discrete value. Right? So a discrete value meaning it's either going to be yes or no, right? So there's nothing in between. We can also predict whether the image that we're seeing is of an aeroplane or a car, right? So this essentially is going to be discrete as well, except we're going to have car or plane, right? So we can also predict what is on the top right of a scenic image that we're seeing, whether it's a tree or a bird or a cloudy sky, right? So we can predict different things. We can also predict how many topics we can categorize a document in. Right? We can predict what the user wants to read next. So all of these different types of things we can predict, and essentially they all fall into a couple of different areas. For instance, we can have regression, right? So regression is going to be the idea of predicting real values, right? So continuous values. And we can have classification. So classification essentially means that we're going to have discrete values. And we're going to start with regression. In general, regression and classification fall into the general category of supervised learning. So what we're going to do is we're going to take some sort of data and we're going to teach the machine. So what it means is that the machine is going to have a teacher and the machine is going to act as a student. So this is the easiest machine learning algorithm to get started with, or the paradigm to get started with. Unsupervised learning has shown a lot of potential, but that's not going to be covered in this particular course. Anyway, so let's start with the learning process. What happens in supervised learning? As I mentioned, because it's supervised, we're going to have some sort of data through which we're going to teach the machine. So what we do is we take the data and we split it in two portions, right? So we take one of those portions and we essentially create a training set, right? So this is going to be called a training set. A training set essentially means that this is a set of data points, right? So let's say we have 100 data points in our data set. So we take 70 of these, and the set of these is going to be called a training set. Now what we do is we take this training set and we feed it to some process. So we're going to treat this as a black box at the moment. Right? So this is a black box, which means we're not going to concern ourselves with how this works, right? So there's going to be some process, and that process is going to give us an age, right? So this age is a function in the sense you can think of it as a programming function for the moment. And what it does is it takes an input and it produces an output. Remember this portion over here that we left out? Now we're going to take this portion over here and treat that as a test set. So this is going to be the exam that we give to the machine. So this portion over here was us training the machine in order to help it predict the outputs given the inputs. Now we take some of the inputs. These are the test set data points. What this means is we never showed the answer to these data points to the machine. And now we feed it to this edge function, and this edge function is going to make a prediction. Now, if this prediction matches with our real values over here, the values that we know are true, right? So the values that we know are true, those are called ground truths, right? So a ground truth is the value that we know to be true. So for instance, I can say that a house that has 5 bedrooms goes for $10,000, right? So that's not realistic, but let's assume I'm in some cheaper market. So I show it this number over here. So 5 goes in, and this edge produces, let's say, 980 or $9,800, right? So it's not accurate, it's not correct, but it's good enough, right? So what we're going to do is we're going to take this prediction and compare it with our ground truth. So this over here, 10,000, is our ground truth, and we're going to compare it with the prediction. If the prediction and the ground truth are close together, so if the ground truth is close to the prediction, we say that the machine has learned, right? So if not, then we need to train the machine a bit more, or we need to change our process over here, pick another process, right? So that's essentially what happens. Now, once you have this edge over here, you no longer need the training set and the process because we have the edge, right? So now this edge is a function, and we can take our test set and we give it to edge, and it can make the predictions. We don't need the whole portion over here. Now this is going to be really important when you do practical machine learning, because this portion over here is going to be compute intensive. You need heavy machinery to carry out this portion over here, right? So this is going to be very, very, very difficult on a mobile, for instance. But once you have edge, this is a very lightweight function, and this lightweight function can be deployed on an FPGA. You can deploy it on a mobile device, you can deploy it on Raspberry Pi, any machine that you can think of, really. So you don't even need the data set anymore, right? So all you're going to have is an edge over here, and eventually you even get rid of the test set and your predictions, right? So all you have is an edge, and you can deploy that edge to another machine, right? So now this looks a little bit intensive, but what we're going to do is we're going to move ahead and give you an example of regression, right? So we're trying to predict a real valued output, and in this real valued output problem, we're going to have a continuous output, and we're going to take the example of housing prices. So this is a very common example in machine learning, and it's very easy to understand because it has only one type of input that we give to the machine, right? So in the next video, we're going to take a look at regression and how we can apply this process over here that we just saw in a lot more detail. Stay tuned. All right, so we're back after the break. We're going to take a look at the example of regression, and we're going to start from the very scratch and look at every detail that we need to know. So we're going to have this data set. So this is our data set, This over here is our input, right? So we're only going to give the machine one input, that is going to be area of the house in square feet, and we're going to give it a number of examples, right? So these examples are going to be called data points. So we have our data set, our data points, we have our inputs, and this over here is our output that the machine is supposed to learn to predict. So for instance, we have these three examples over here. We can take two examples and we can put this in the training set and take this over here and we're going to put it in the test set, right? Obviously, if you're going to have a real machine learning algorithm or an example, we need to have these like 30,000 over here and 20,000 over here, but the concept is going to remain the same, right? So we take this data set over here and we take some of the points as training set, and then what we do is we go over here and we plot it, right? So on the x-axis we're going to have our area, and on the y-axis we're going to have our price. So first, let's try to think about the machine. What the machine first does is it takes the price and the area and it plots all the data points that we showed it, right? So these values you can ignore for the moment. It's not really important what the exact values are. You can get rid of these, and you can plot all of the different values that we have in our data point over here, right? So once we have these different data points over here, what we want to do is we want to predict what the relationship is between the area and the price. If we know what the relationship is, what we can do is we can simply plug in the area in that relationship equation and get the price out. Seems fairly straightforward, right? It's not that straightforward, but it's a good enough approximation to start with. So let's assume first that the relationship between the area and the price is linear, right? So what does that mean? It means that the price is equal to some number a plus b of area, right? So we multiply the area by some number and then we add some number and we get the price, right? So this is called a linear relationship. Now, since this looks a little bit too long, what we're going to do is we're going to change this price to y, right? We're going to change this area to x, and we get the simple equation of y is equal to a plus bx. Now, this is the straight line equation. Straight line equation, right? And these two things are what we need to figure out. We already know all the x's, we already know all the y's, right? So we got them in the data set over here. Now what we need to do is find out what a and b are, right? So what this does is, for instance, like let's take two values. Let's assume that the value of a is equal to over here, let's call this 25, and let's say the slope of this line is, let's say, 2.9, right? So the value of a is going to be 25 and the value of b is going to be 2.9. So this is the slope. So b over here is the slope. So let's go ahead and annotate that, right? So this over here is the slope. So this basically says if we change x, how much is y going to change, right? So if we change x by 1 unit, how much is y going to change? So let's say if b is 2 and we have a is equal to 4, right? So it is going to be 4 plus 2 into x. So that's an example. Y is equal to 4 plus 2 into x. So if x was 2, we're going to have y as 2 into 2 is 4 plus 4 is 8. If we change this to 3, this is going to be 3 into 2, 3 into 2, which is going to be 6 plus 4 is equal to 10. Right? So what this says is if you change x by 1, y changes by 2, and that is going to be the slope over here, which is b, and the value of b is 2, right? So I apologize if I'm boring you with all the details, but it's really helpful if you understand this theory a little bit, right? So you can skip ahead if you find this too easy to understand, right? So anyway, let's go ahead. So we got this slope over here and we got the a, and this a essentially means that if you set x to 0, then where does the y stand? So if x is equal to 0, y is going to be over here, right? So this is the y-intercept. Anyway, so let's get back to our line over here. So we have this line over here, and if you look at this line, it does not look like it's a good fit for these points. Right? The points are going somewhere else. If this was our prediction and we wanted to predict the value of y over here, this would be our prediction, whereas y is way over here, right? We'd be wrong for almost all the different points, right? So these will be our predictions, and almost all of the points are way far away from our prediction. So what we want to do is we want to figure out a way of changing this line from here to, let's say, over here, right? So this looks a lot better. Still, our prediction is going to be off for this guy over here, and it's going to be off for this guy over here, and this is going to be off a little bit here, a little bit here. So we still have problems over here, but as you can notice, the problems aren't all that bad, right? So over here, this individual was all the way wrong here, right? So this is very wrong. This is very wrong. A lot more wronger than over here. That's not a word, but you know what I mean, right? So anyway, which one is better? You tell me. It looks to me like this guy over here is better, right? So let's go all the way back over here to our definition of machine learning and realize, right? So better, what is better, right? So we said according to some measure. Let's go over here and find out what the measure over here is. Let's formalize our thinking. What are we saying? Why are we saying that this second line, this blue line, is better? It's better because these lines over here, the error lines, the difference between our prediction and what the real world data says, those are smaller, right? So the smaller the lines, the better the fit, right? So that's why we use the word fit over here. So we're fitting the line. So let's write that over here, fitting the line, right? So or fitting the line over the data points. Now, what we have over here are some errors. Let's collect these errors in a specific formula, right? So let's go over here and say, let's take this one point over here. So this is our prediction over here. Let's call this y prime. So we have y prime over here, right? And what we're trying to do is we're trying to find out the difference between these two, right? So y prime minus the y. So this over here is our y prime. So this is our prediction. And this over here is our real world value, the one that we got from our data set, right? So now we have our prediction and the real world value, which is our ground truth, the expectation. So whatever the difference between these two is. Now, if this y is more than the real world value, it's bad. If it's less than the real world value, it's equally bad, right? So we don't care what the difference between these two is. So what we can do is we can go ahead and square it. So if we square it, if we got this number to be, let's say, -2, this is going to turn into 4. And if the number was 2, this is also going to turn into 4, right? So we get rid of the, essentially the minus sign over here, right? So we'll come back to why we need that in a minute. So now we have this difference between our prediction and the expectation. We also want to consider all of the different points. So what we're going to do is we're going to sum over from I is equal to 0 to m. So this m is going to be the number of data points that we have. So number of data points, right? So this is our number of data points, and we're going to sum over all of these different things, right? What if we have 1,000,000 data points? This value is going to be quite large. If we have only 10,000, this value is going to be small. So what we want to do is we want to take away this m effect over here and multiply that by 1 over m, right? So now we have an equation over here which essentially gives us the specifics of this better. So if this value is small, we're going to say that the lines are better, right? So if we draw a line and then we compute this whole thing over here and it gives us, let's say, 20 minus 20 plus 20, and then we draw another line and that gives us 40, we're going to say that this line is better. Why is it better? Because the errors are much smaller. The aggregate of the errors, or the average of the errors, or the mean of the errors. Which errors? Squared errors, right? So the mean squared errors are much smaller, and that means that it's a better fit, right? So this is called a root mean squared error. Okay, so if you put an under root over there, sorry, If you put an under root over there, that is going to turn it into a root mean squared error, or you can just say mean squared error, right? Now that's a lot to take in, but that covers a lot of the ground in terms of understanding machine learning. So make sure you go back and understand all of this. If you have any questions at all, please come back to me, ask me questions. I'd be happy to help, and make sure you understand this. If you understand these portions over here, machine learning and code and everything else is going to be a lot easier for you down the line. Let's summarize this and finish off this video. So what we're going to do is we're going to change our A's and B's to theta 0 and theta 1, right? So these are essentially A and B, the same thing, right? So no difference. We're just calling them theta 0 and theta 1 because we're going to have quite a few, and essentially they're going to go into a very large number greater than 26, so alphabet is not going to be enough for us. So these two things over here, these need to be identified. This x, remember, is fixed over here. This over here is what we called y prime, right? So this is our prediction. So let's call it h theta of x. So let's decode this. H is for hypothesis. Our hypothesis, given the values of thetas, which are over here, for a particular input x. So this is going to be equal to y prime, right? So this over here, this whole thing over here is our what is called a model. Right? So this is a model. These are the model's parameters. Right? So this is obviously the input, and this is our prediction. And what we're trying to do is we're trying to fit the model. And what that means is we're trying to find the values of these model parameters such that our error is minimized. Right? So our error is minimized. That's what we're trying to do. So we have fitting, we have prediction, we have our parameters, and we have our model over here. So that is essentially all the terminology that you need to have in order to understand machine learning literature. All the other things will come along as we proceed with our course. In the next video, we're going to take a look at how we can change this real valued output into classes, and then cover the more interesting areas of machine learning, such as classification. All right, so in the last video, we took a look at regression, we took a look at the terminology, and we predicted some real valued outputs. Right? So now what we want to do is we want to go ahead and do a little bit of classification. So what we want to do is we want to predict a class. So what that means is, if you remember the example that we did earlier on for scikit-learn, we wanted to predict whether this image, this guy over here, whether it's a 0, a 1, a 2, or a 5 up to 9, right? So which one of these is it? So obviously we know that this is a 5, but does the machine know? So this is an example of classification. So what we want to do is we want to predict a discrete value. Saying that this number is 1.5 will make no sense, right? So we can only have zeros and then a jump, 1, 2, up to 9, right? So discrete values. So this is called a classification. Now you can have different types of things. We'll start with the basic, and we're going to say that we're going to predict whether a class, an input data point, belongs to a class or it does not belong to a class. For instance, you show the machine an image and it says whether it is a cat, yes or no, right? So yes or no answers. So this is called a single class classification. Or simply classification. You can also have this scenario over here in which we ask which class does it belong to, and this is called a multi-class classification. Right, so multi-class classification or simply classification, right? So you can have different types of things. Let's start with this guy over here, right? So we need to make two changes to our process of regression. Right? So remember last time we did regression and we predicted real values. Right? So for instance, the price of the house, it could have been 29.69. That would have made sense, but in classification this is not going to make sense. So we need to make two changes to our processes. let's draw our current situation over here. So we have this process over here, and I'm going to draw a line over here because we had this guy as a linear equation, right? So we're going to draw this as a straight line over here. So this is simply a symbol over here, and what we gave it as an input was an x, right? So some input, and it predicted some y for us. But we also had some model parameters over here. So we had a theta over here. So given an x and a theta, it would predict a y for us. Now, what we want to do is, first of all, we don't want this as a linear equation over here, because if what we get out of this, if this is a linear equation and we give x, for instance, I don't know, let's give it a 50,000 as input, and theta was, let's say theta 1 was 2, we're going to get a very huge value out of it, like 100,000. Right? So if you don't understand that, please make sure you go back and put it in the equation so that you know what I'm talking about over here. So what we have over here is a very large value. Now what we want to do is we want to predict whether something is or is not in a class. And for that, what we want to do is we want to make sure that we fall in a specific range, which is 0 to 1. Right, so this comes from probability, but you don't really have to understand it at the moment. We want our output to be constrained between 0 and 1. So if we have the output somewhere over here and it's less than 0.5, we're going to say no. And if it falls somewhere over here or here or here, we're going to say yes. Right, so all of these portions over here are going to be yeses, and all of these are going to be no's. Right. So for that, we need to take this number and we want to squish it between 0 and 1. So there are a lot of squishing functions. So these are called squishing functions. And let's take an example of one over here. So this is a sigmoid function. So this is the origin 0, 0. And this over here is plus infinity, and this over here is minus infinity. So this x-axis is the input value. And we give, let's say, this input value, this function, we give it a minus infinity, it's going to return a 0. Right? So if we give it plus infinity, it's going to return a 1. In the middle, it's going to show this behavior, right? So it's going to have a slightly gradually increasing line, and this function is called a sigmoid, right? So let's make sure we understand this. Let's say we got as an output over here minus 100,000, so that's going to be way over here, right? So we're going to get a very small number over here. So this is, I don't know, let's call it 0.001, right? If we gave it, on the other hand, a 0, let's say this y was predicted as being 0, so this is going to go over here, and this specific value for sigmoid is 0.5, so we get 0.5 out of it. Let's say if we gave it a very large number, let's say over here, let's say 10,000 that we had earlier, this is going to give us a number very close to 1. Right, so now we are squished between 0 and 1. We cannot have a value larger than 1 because this sigmoid does not have a value larger than 1. Right, so we have taken this linear equation. So what we have now over here is the same guy. So we're going to predict our linearity, right? So this linear function is going to predict something, and then we're going to squish it. So that's how we draw it. So you might have seen these symbols in machine learning literature or in deep learning codes. So this is what we draw over here, because we have taken this y output and we have squished it. Now once we squish it, we're going to predict a 0 if this value after being squished is greater than 0. Is less than, sorry, let's make that less than. If it is less than 0.5, we're going to call it a 0. If it's greater than 0.5, greater than or equal to 0.5, we're going to call it a 1. So now what we have is this process no longer outputs a real value, right? It outputs either a 0 or a 1. Why? Because we have a 0.5 over here and a 0.5 over here, and we have squishing over here, which produces a value between 0 and 1. Right, so now we have this squished function over here, and this is what we call classification. So the process remains the same. We give it some x, we give it some thetas, whatever the value is produced, we're going to change this to fall within the range of 0 and 1, and then we're going to see if the value is greater than 0.5, we're going to say yes, so this guy over here. If it's less than 0.5, we're going to say no. So is this a cat? If we come over here, we say yes, it's a cat. If we come over here, we say no, it's not a cat, right? So that's essentially what classification is doing in terms of regression. Obviously, our error is going to change, but we don't have to worry about that right now. So now that you have this one building block over here, let's go ahead and combine a couple of these. So we have this guy over here, and we have an x going in, and we have a theta going in. So let's leave this guy over here and come over here and create another theta, another squishing function. So this same x is going to come over here, right? So we're going to input the same x to here, but we're going to have a different theta for this guy, right? So because this theta and this theta are different, let's call this 1 and let's call this 2. Because these two are different, this is going to produce different behaviors, right? So these outputs are going to be different. Now, when we have these different outputs, what we can do is we can take these and plug them in to another squishing function. And what this is going to do is it's going to take the output of these guys and treat that as the input, and it's going to produce its own output over here, right? What this does is it takes this x and decides some sort of behavior of x, and this guy decides some other sort of relationship between x and the output. And based on these two different outputs, this guy is going to give them weights. Think of it this way. This guy over here is our senior detective, right? So now the senior detective is really good at solving crimes. But how does he work? He takes some information from the medical examiner, who is capable of dissecting the body, finding out what chemicals are in the body, and all that biology stuff, right? So I'm not sure what that is, but a medical examiner essentially performs the autopsy and finds out the cause of death and all that stuff. This guy over here is our detective, right? So the junior guy who goes out and collects the evidences from the scene, talks to the witnesses, all that stuff. So this guy is not aware of the information that is over here, and this guy does not know what the detective is doing, but they both provide some input to the senior detective, and this senior detective has some of its own parameters over here, right? So it has some of its own parameters over here, and based on those two parameters and the inputs that it is getting from the two different sources, it's able to make a good decision, right? So let's call that a good decision, right? So think of it this way. A two-level machine that we have over here is somehow divided into low-level information and these two are not going to communicate with each other, right? Whereas this guy receives information from all of them and can make high-level decisions, right? So this guy can make high-level decisions because it's able to offload some of the work to the low-level workers, right? So essentially what we have over here is a deep network. Now you'll see where the concept of deep neural network comes from. So this over here is a deep network because we have, well, it's not technically deep at the moment, but we'll make it deep in a minute. So we have this guy over here, and then we have this guy over here. So it's a deep hierarchy, right? So we have this guy, and it's talking to these two people, and this guy in turn is talking to these two guys, and this is talking to these two, and so on and so forth, right? So it becomes a very deep hierarchy. And if you turn this around, this is going to turn into this guy over here. This leads to deep neural networks and deep learning. So this is what we have over here, removing all the thetas. So this guy over here is our x. So x can have different values. We only have one feature earlier on, but now we can have 1, 2, 3, 4, 5, 6, 7, 8 different values going in. And this is our medical examiner. This guy over here is our detective. This guy over here is probably some other agency that can provide us more information. And this is one level deep, and then we have further down the line, and finally we have some output over here. This one guy over here, this is the senior detective that says that yes, this is a cat, and I'm fairly sure because I got the value out as 0.8. Now this guy over here is another senior executive, another senior detective, and based on all the different values that it got from over here, it decides that it's a dog. Now he says that this is with a confidence of 0.7. This guy says that it's a car, right? So car, but he's not really sure, right? So let's not worry about him. And this guy over here says that it's a let's say a bear with 0.6. Right, so now we have these four guys over here, and everybody says, like, this guy does not say that it's a car, right? So it's less than 0.5, so this is out of the race. But we do have these three guys over here, and this is saying 0.8, this is saying 0.7, this is saying 0.6. What we do is we take the max, and we say, because this guy is the most confident, this is most probably a cat. Right, so that is what we have over here in terms of making the final decisions, and this is called a softmax. So max, I already explained, it's called a soft because we do a little bit of computation over here, but that's not really important. What's important is that the output, the maximum output that we get out of it. So after squishing, we don't apply the threshold. What we do is we simply output the value. Instead of saying yes or no, we say 0.8, and whatever the largest value is, we pick that as the class. So now this, we have multi-class classification. Multi-class classification. Instead of just one class, now we can predict many classes, and we have the softmax. So these two new concepts have been introduced on this over here. Now, because we have this guy and this guy over here, and also over here, this is our output, and this is our input. We have what are called hidden layers, just as we had a hidden layer over here. So this was our hidden layer. And if we have more than one hidden layers, these are called deep neural networks. So there you have it, deep neural networks in half an hour. Now, I have skipped, obviously, a lot of theoretical details, but this, if you understand all of this completely, this should be sufficient to get you started with quite a lot of code. Let's quickly recap what we've seen in the past couple of videos. So we started with this basic understanding of fitting a line or a model by manipulating the model parameters. And the idea was to reduce an error at the end of the final model so that we have the optimum values for the model parameters. So that's essentially called fitting the model, and that is what we did over here in this basic theory portion of our code. Then we went ahead and decided that we wanted to do classification, which is a yes or no answer either for one class, which is called classification, binary classification, or for multiple classes, which is multi-class classification. Then we saw how this classification model, simple classification model, can be used in conjunction with other models to convert it into a deep neural network, which is able to make high-level decisions as opposed to the simple decisions that can be made by a basic classification model. Finally, we took a look at how we can create deep neural networks by having multiple hidden layers. And we took a look at the multi-class classification. Now, as I mentioned again and again, this course is only an introductory course, and we don't want to go into the theory too much, because I have seen again and again that when you're just getting an introduction to machine learning, going into too much theory without code really hurts your progress. So in this course, we're going to keep the theory to a minimum, and that is essentially all the theory that we're going to do. However, when you're done with the course, you do want to understand the mathematics behind the machine learning models if you really want to get an understanding of that. So what I'm going to do is, I'm not going to cover the details of the theory within this course, but once you're through this code and you have gone through all the codes that are necessary for the understanding of deep neural networks, I want you to go back and take a look at this deep learning talk, which was a very applied talk that I gave last year. This is available completely free of cost if you go to this URL, bit.ly/prac-ml. So this is a talk given by me to a university audience, and this is a little bit math heavy, but it covers all the mathematical background that is necessary to go from what we have in this course up to whatever is necessary for understanding everything else. right? So I highly recommend that you go over there to this URL and take a look at the approximately 1.5 hour free talk, which takes a look at all the mathematical details that we've missed in this course. So again, it's free. You don't have to pay for the video. You just go over to the URL and watch it. So I highly recommend you do that after you have gone through this course in detail.